Okay, so some examples. These first ones just say to check that or verify the given value of x is a solution of the equation, so we're just plugging in the value and seeing if it's true. So number 4, pi secant of x plus pi is equal to 0, and they tell us that x is equal to pi. So we're plugging in pi for x and then solving to see if it works. So pi times the secant of pi plus pi, and we want it to be equal to 0, so the same thing, we're just bringing the 0 down. So what's the secant of pi? Or what's the cosine of pi? -1. So secant is 1 over cosine, so we have pi times 1 over -1, so times -1 plus pi. So this is negative pi plus pi, which is 0, is equal to 0. And then if we had something that's a little bit harder, but same problem, like same instructions. 3 times the cotangent to the 4th of x minus cotangent squared of x minus 24 is equal to 0, and x is equal to 7 pi over 6.
When I saw that to the 4th, I was like, okay.
So it looks a little scary, but this is what I would say to do first. Yes, you're ultimately plugging it in, so you could draw that you're plugging it in or like write it in. So you could be like, okay, 3 times cotangent to the 4th of 7 pi over 6 minus cotangent squared of 7 pi over 6 minus 24. But what I would do here is I would do like a little pause, and I would just find out in general what the cotangent of 7 pi over 6 is before you go too far. Now, cotangent is the same as what? Okay, 1 over tangent. So 1 over the tangent of 7 pi over 6. So what's the tangent of 7 pi over 6?
Oh, that's 4.
Square root of 3 over 3.
Square root of 3 over 3. So this is 1 over the square root of 3 over 3. So keep, change, flip. So this would be 1 times 3 over the square root of 3, which is going to be 3 root 3 over 3, or just root 3. Okay? So the cotangent of 7 pi over 6 is the square root of 3. So now I'm going to replace cotangent of 7 pi over 6 with the square root of 3. And then I'll just be raising it to the 4th power, whatever. Because remember, I think I mentioned this yesterday, but because I'm doing literally the same thing in 2 different classes, I can't keep up. Cotangent of 7 pi over 6 raised, all of this raised to the 4th, is the same as cotangent to the 4th of 7 pi over 6. These mean the same thing. So I can take this value that I found for the cotangent of 7 pi over 6 and then just raise it to the 4th, square it here. So I'm going to have 3 times the square root of 3 raised to the 4th minus the square root of 3 squared minus 24.
How did we get the square root of 3?
From solving for. So we did 1 over tangent.
Mm-hmm.
So tangent is root 3 over 3.
Yeah.
So then I did keep, change, flip. So it was 3 over root 3 times 1. And then I just rationalized that. So I did the 3 root 3 over 3, which reduces to root 3.
Okay.
That was that intermediate step there that I just didn't write.
Oh. Where you did on the side with the square root of 4 thing, like they kind of did out to the side, is that part of the problem, or were you just showing them?
No, I was just showing you why I can rewrite it this way.
Okay.
because some people get confused about that this is cotangent to the fourth of this. But it's like, really, it's cotangent of that all raised to the fourth.
Okay.
So, which, again, is more of a later trig thing that is where you see it more, but it means the same thing. It's more like once you get to calculus, it's important to know this fact because of things that we do in there that I prefer to rewrite it this way if it starts out this way, just because it's easier to see. You got 2 years for that, but still. So the square root of 3 raised to the fourth would be what? You don't need a calculator for that. 9.
Boom.
That would have been my guess.
Square root of 3 squared would be 3. Then
Oh, yeah.
3 times 3 is 9, so 9.
I just
Minus, so the square root of 3 squared is
3.
3.
I saw Josh pull his calculator. I was like, okay.
I just wanted to verify myself. You know, I make mistakes.
So this is 27 minus 3 minus 24. 0 equals 0, so that's good.
It's gonna be even funnier if we in fact did need a calculator for it and I just yelled out 9.
No, see, you shouldn't need a calculator for something like that. No offense to anyone who pulled out a calculator, but shouldn't need a calculator for that.
Well, I thought it was 9, but I wasn't 100% sure.
To be honest, I had no idea what it was. I'm still thinking about biology.
Fair enough. All right, find the general solution of the equation. So the problem is the square root of 3 times the cosecant of x plus 2 is equal to 0. So you may be like, what the heck are we doing? Okay, we're solving for x. So we have to undo everything to get to x on the left, everything else on the right, and get an answer. So I would subtract 2 first. So the square root of, oops, I'm going to change colors. So square root of 3 cosecant of x is equal to negative 2. Then I can divide by the square root of 3. So cosecant of x is equal to minus 2 over the square root of 3. Now, there's a couple ways you could think about this. But what is a way that I can rewrite cosecant?
1 over sine.
1 over sine. See, this is where I'm saying it comes in handy. 1 over sine of x is equal to minus 2 over the square root of 3. I want sine of x on top, though, to solve. So, look, watch this. These are both fractions. They're equal to each other. So I can flip both of them. It'll give me sine of x over 1, but I don't need to write it, is equal to the square root of 3 over negative 2. Do we see what I did? I want to make sure. Okay. So now, this is where the inverse trig stuff comes in. Okay. X is equal to the inverse sine of the square root of 3 over negative 2, or minus the square root of 3 over 2. So,
Do we need the calculator now?
oh, this is funny. Okay. I'm going to have to explain this, and you're going to be like, why'd you confuse me? I'll explain in a second. On the unit circle in general, ignore the general rules of inverse trig, because I forgot when you're doing general, you don't do that. Where is sine minus the square root of 3 over 2? Just give me the exact value as you see it on your unit circle. Ignore everything I said earlier.
Pi over 3.
Negative square root of 3 over 2.
5 over
Wait, what did...
Pi over 3.
Okay, 5 pi over 3 is one of them. Where else does it occur?
4 pi over 3. Is that what you said, Virginia?
Is that what you said?
6. I said that.
Oh, I thought you said pi over 3. Sorry.
I thought I just had it written wrong. I was like,
Okay, so 4 pi over 3 and 5 pi over 3. Okay, I forgot what these ones, because we're doing general, you don't. The rules of inverse trig do exist, but when we're doing these, you have to write the actual value, because it's every time we hit there is the solution to the equation. So, x is equal to this, but it exists here more often than that, so this is where the plus 2n pi comes in. Anyways, so yes, please ignore what I said about this. This is still true, but it doesn't work like that with solving them like this. We use the actual value and then add the 2n pi to them. Let's see. And if it's on a specific interval, then we're doing it on the interval that they tell us. So like when we get to the more specific ones, we'll do it on those. Let me see. Let's do probably one more for today, and then we'll finish it tomorrow. 12 sine of x plus the square root of 2 is equal to minus sine of x. So I need to get all my x's on one side. Since I like things on my x on the left, I'm going to move this over, and then I'm going to move this over here all on the same step. So I'm adding this, so 2 sine x is equal to negative square root of 2. I'm going to divide by 2, so sine of x is equal to minus the square root of 2 over 2. Gracious. So the inverse sine of minus root 2 over 2. So where does sine equal minus the square root of 2 over 2? Should be in two spots. 5 pi over 4 and 7 pi over 4. And then we add, because it's sine, 2n pi. And technically speaking, minus 2n pi as well, but we are assuming that n could be a negative number, which is why we just say plus 2n pi. All right, since that one was fast, I'm going to go ahead and do a tangent one real quick of the general, and then we'll save the specific ones for tomorrow. So I also need to look, because for some reason only one of my specific problems printed, and there's a lot more in this section than that, so I need to check on that. All right, 14. 3 tangent squared of x minus 9 is equal to 0. So what should I do first? Move the 9 over, so 3 tangent squared of x is equal to 9. Then what?
Divide by 3.
Tangent squared x is equal to 9 divided by 3 is 3. Then what?
Square root.
So this is another reason why I show you that this square's on the outside, so that you know, like, you're taking the square root of the whole thing. So tangent of x is equal to the square root of 3. Now, when we take the square root, what do? If I said x squared is equal to 4, you would tell me that x is equal to what? Same thing occurs with trig functions. It's plus or minus the square root of 3. So I have, because I'm going to have two different sets of solutions, tangent of x is equal to the square root of 3, or tangent of x is equal to minus the square root of 3. This right here is why it's not 2n pi for tangent. Okay, because when we go to do it, it's going to be in two places 180 degrees apart that you get the same value. That's what I was trying to explain earlier, and I wasn't explaining it very well. But there are two places on the unit circle where tangent is positive square root of 3, and two places that it is minus the square root of 3. And they happen to be 180 degrees apart from each other. So where is tangent equal to the square root of 3?
Pi over 3 and 4 pi over 3.
Okay, so I want the most general one. So I want the simplest one. So pi over 3 plus n pi, because adding n pi gets me to 4 pi over 3. If I add n pi again, it gets me back to pi over 3, or whatever the increments of that are as you go up. Okay, so that's for that part. Then for minus the square root of 3, where's that? 2 pi over 3. So again, it occurs around again farther, but we care about the most basic one. So x is equal to 2 pi over 3 plus n pi. So tangent is always n pi, sine and cosine are always 2n pi. Because to get that value, you have to go all the way around. Not that it doesn't exist twice, but you have to go all the way around to get back to that same equivalent. Okay, you can't, there's nothing that you can add consistently to get there without having it as two separate things. Because 5 pi over 4, if I were to add whatever it takes to get to 7 pi over 4, but then I add that value to 7 pi over 4, that's not getting me back to 5 pi over 4. Because it's not a perfect amount around, like, evenly. So that's why we do each of those separately. Like that. Basically, when we get to the specific ones, just to kind of give you a preview, what's going to happen is it's going to tell you that we're solving on the interval 0 less than theta less than 2 pi. And so any place that that value is true in that interval, we write. Okay, then we have to check them to make sure that it still makes a true statement, because just because it exists doesn't mean that it's true. So that's where the solve and check part comes back in. And then we might do a little bit more with some harder equation solving, but that would still be general. So I need to go back and look and see how much I normally do with this section and go from there. But anyways, no homework today.